equation. Or you could even give me an example of an expression. If I said 2x plus 7, is that an expression or an equation? Oh. So if I said 2x plus 7, is that an expression or an equation? It's an expression, okay? So how could I write more to make it look like an equation? Equal sign. So if I said on this, if I said 11, that is an equation, okay? I could solve that to figure out what that's going to be, okay? I could subtract 7, okay? But then the solution is x is 2, and it's only 2. That's the only answer it'll be. But now if I were to look at a function, if I said, well, y equals 2x plus 7. If I have a function y equals 2x plus 7, there's multiple x's that I could have. I could say, well, if x is 2, I get 11. If x is 0, I get 7. If x is whatever, I can come up with it. And the key thing with a function, you can graph it. Okay, so 2x plus 7, I'd have a y-intercept here at 7. I go up 2 over 1. So I'm going to get something that looks like this, and it's going to continue on. So that line on a graph represents all solutions that I could have. No matter what I pick for x, I will get an output y. All right, so that's a function. So we're going to start talking now about functions rather than the specific equations. An equation, it's only one answer, okay? Or if we have a quadratic, we have more than one, okay? But a linear equation, there's one answer. This is the only x that'll work that we'll get, for this case, we'll get 11, all right? And then we're getting into interval notation, representing solutions with number lines, relations, and then domain and range. So for that worksheet today, you're going to be able to practice. I'm going to ask you to identify the domain. I'm going to say, is this a function? And so on. All right, so interval notation. All right, this is important. It's just another way of representing a solution set. Let's talk about as an inequality. If I were to restrict my x's, and I say 0 is less than or equal to x, which is less than 5. If this is the set of x's I'm looking at, this is one way to represent it, but a second way is with interval notation. Okay? Well, I know what this means is I could have 0 as an x value, because x has to be greater than or equal to 0, so I know I could have 0. I could have all the decimals in between. I could go 1, I could go 0.1, I could go as far as I want to go, but I'm basically going to go all the way to 4.999 repeating. I will never reach 5. I can never be at 5. Okay, I only want x values that are 0 inclusive all the way up to 5 non-inclusive. So how we write this in interval notation is I could say 0, 5. So do not get this confused thinking it is a coordinate. I'm talking about x, the interval of x. A parenthesis means I am going to, back that up. A bracket means that I am going to include 0. And so as silly as it sounds, I think of a bracket kind of like it's hugging the number. I'm including that 0 in there. All the way up to 5, and I'm not going to include 5, so I put a parenthesis around it. Okay, so kind of like my arms are wide open, I'm pushing somebody away, I'm not including them in my hug. Okay, so bracket is inclusive, a parenthesis is not inclusive. Okay, and so if we were to think of this with inequality notation, like we'll say less than or equal to or greater than or equal to, Whenever you see that, that means inclusive, and that will be represented with brackets. Okay, and it can go either way. If you see an inequality that is simply greater than or less than, that is not inclusive. And that's when I will use parentheses around just that number. So we can have a mixture. We could have both parentheses, both brackets, or we could have one and not the other. I could also represent this interval with a number line. And so if I'm going from 0 to 5, I would do a filled in circle at 0 and then an open circle at 5, and I would shade everything in between. All right, so that'd be the same way that I could represent my interval from 0 to 5, inclusive with 0, not inclusive with 5, on a number line with circles or not. Closed circles versus open circles. Okay, another thing, we could sometimes have a interval that goes from negative infinity all the way to positive infinity. That could be an interval to work with. Infinity are always with parentheses. So we're always going to use parentheses around infinity. All right, we're never going to include infinity because we can never reach infinity. Could also represent this with an R with 2 vertical bars, and that simply means all real numbers. So say I had an interval, say I was going from 0 to 2, well, let's go from 0, I got it backwards now. Let's go 0 to 2. And if I know that I want my interval to be from 2 to infinity, that's going to look like an open circle and continuing on this way. So we're going to go back and forth from interval notation to maybe number line notation to some inequality notation. They all mean the same thing. It's just simply how we are writing it. Okay, so let's do a little practice here. Draw each inequality on a number line and write in interval notation. Okay, if it says x is greater than 6, so I know on my number line, I'm going to be here at 6. I'm not going to include 6 because its x value is greater than, so 6.0001 is where I'm going to start, and then it's going this direction. So x has to be greater than 6. If I were to write this in interval notation, I would have a parenthesis around 6 because I'm not including 6 all the way up to infinity, and then always a parenthesis around infinity. I said x is less than -5 or less than or equal to -5. Put -5 on my number line. This one, it can be -5, so I'm going to fill that in with a circle. And then I'm arrowing to the left because I want x values less than -5. And sometimes it might help you to think of actual numbers, okay? X has to be less than -5. I could go like -6, -10, -15. All right, I'm going left. I got to make sure I shade left. So this goes all the way out to negative infinity. You don't have to label negative infinity on your number line. An arrow continuing on in that direction tells me it's going towards negative infinity. But sometimes writing that in will help you remember, okay, this is going, when I read from left to right, negative infinity all the way up to -5, parenthesis around infinity every time. But I'm going to include -5. Now the last one says -7 all the way to 2. I'm inclusive at -7, but I'm exclusive at 2. So a solid circle at -7, open circle at 2, and it's everything in between here. So my interval would go from -7 to 2, parenthesis around 2, bracket around -7. Okay, for practice now, let's go from interval notation to write it on a number line and then as an inequality. So +4 all the way to infinity. All right, I know I'm going to be here at 4 and I'm shading to the right. Okay, you don't have to write infinity, but just for visual reference, the arrow going out to the right means it's going all the way to infinity. 4 is inclusive, okay? It's hugging that 4, so I'm including 4, so I'm going to fill that in with a solid circle. And then as an inequality, so we can write this as x is greater than 4. You can write it that way if you think of, okay, x value is greater than 4. You could also write it as 4 is less than x, means the same thing. Okay, both of them are saying the alligator's mouth's going towards the x is bigger. So x is greater than 4, you could write it either way. Say x is greater than 4 or 4 is less than x, same thing. Second one here, -infinity all the way to a +2. Yes? Ooh, thank you. Yes. That should be greater than or equal to. Good catch, Abby. Thank you. Yep, it's inclusive, so I'm going to include that. All right, -infinity to 2. So this is my interval that I'm looking at. This is an open circle here at 2. So I can think of this as x values less than 2. Or I could think of it as 2 is greater than x. Or x, yeah, 2 is greater than x, x is less than 2. Whatever makes more sense to you. Okay, it represents the same thing. The alligator's mouth is going to 2. It's going away from that x. All right, the next one from -1 to 0. It's going to be an open circle at -1, a filled-in circle at 0, and everything in between. So this is saying -1 is going to be less than x, but it's going to be less than or equal to 0. And then the last one, -infinity to +infinity. With any number line, put a number with it. So I would just say 0, but it's going to represent everything. So I'm going to exaggerate that. I'll say this represents everything that I'm working with. Can't write this as an equality. I would just say all real numbers or something. Okay, I don't think you'll ever have to represent -infinity and infinity on a number line. But if they ask you something about it, you can just say that R with 2 vertical bars says that's all real numbers. It's anything we can work with. All right, so that was this one was interval notation to inequality. The last slide was inequalities to write in interval notation. And you'll be asked those interchangeably. and pay particular attention to what they're asking. Do they want the answer in interval notation, or do they want it as an inequality? All right, so we could have now some points. Remember, a function is something we can graph. Okay? These points could be represented with a table. All right, so if I had a table, it said, okay, if x is -1, y is 3. Now, this is a coordinate. This is not an interval. This is not interval notation. Now we're back to the idea of a function is something we can graph. What we graph are individual coordinate points. So with this saying -1 and 3, that's a coordinate point. Okay, I could graph that, and I could say, okay, -1 up 3 would be that point there. I could go over 0, up 1 would be that point there. I could go over 1, down 2 would be that point there. I could go over 2, and over 2, down 1 would be like that point there. So all these coordinates I could plot. We can also do mapping, where they draw these circles, kind of egg-shaped circles. And I can map my x to y. If you tell me x, I'll tell you what it's going to be with y. So if we use the same set of x values, it'd be -1, 0, 1, and 2 are my x's. And then I could represent this if I went in order. I could say I'll go -2, -2, 1, and 3. I don't have to write 1 twice. And then mapping is literally showing -1 goes to 3. 0 goes to 1. 1 goes to -2. And 2 also goes to 1. So that would be the mapping. We're going to get into domain and range, but x is that domain, y is the range. I could do a scatter plot, which is basically what I did up here already. It's going to map, put down each point. So 1, -1, 3, 0, 1, over 1, down -2, and over 2, up 1 would look something like that. And then ordered pairs, I can treat each of these because these are coordinates. So -1, 3 would be a point. 0, 1 would be a point. 1, -2, 2, comma, 1. And these are not interval. This is not an interval. This is the actual coordinate point for some function, or for some relation, actually, is what this is. We'll get into the specifics in a minute. All right, so these are 4 different ways that we can represent data, essentially. All right, so, as I said a minute ago, is a relation. A relation is simply any pair of input x to output y. All right, it's basically any coordinate point. All right, so you list me any set of coordinates, and guaranteed, I'll tell you, it's by definition, that is a relation. All right, but now we can get more specific and say, okay, does that qualify as a function? Does that relation qualify as a function? You, like I said, you just give me all these random coordinates. Guaranteed it's a relation, but it's not necessarily a function. To be a function, it's going to have exactly one output for every input. So if we look back at that mapping, there's not going to be 2 inputs of x that go to the same output of y. Okay, a function is very specific. You give me an x, I will tell you there's only one y that it's going to match up with. Okay, it's not saying, okay, well, if x is this, sometimes it goes to 5 and sometimes it goes to 7. That's false. Okay, it has to go exactly one output. And we have the vertical line test. So if we were to graph it, if we were to graph any function, it must pass the vertical line test to be a function. If it fails the vertical line test, it is not a function. Okay, so if I gave you a table and asked, is this a function? Well, I have here 1 goes to 2, 2 goes to 3. So I'm kind of doing this like a mapping at the same time. 3 goes to 2. That's fine. Okay, because 1 went to 2, 3 can also go to 2. 4 goes to 3, and 5 goes to 2. Okay, that's all good. Okay, if there was like another line here that said 5, comma 3, well then that's saying that sometimes 5 goes to 3 and sometimes 5 goes to 2. That's when it would fail. Okay, but as is, yes, this is a function. Okay, it goes to exactly one output. Okay, 1 goes to 2. It's not 1 goes to 2, then sometimes 1 goes to 3. There's no choice on this. It has to go to exactly 1. But having multiple y's is fine. Like there's 2's and 3's on there, but the first 2, 1 goes to it. The second 2, 3 goes to it. All right, the x's are different. That's good. If we set it up here with mapping, and again, we'll say this is our x and this is our y. All right, this 7 is causing a problem because we're giving 7 the choice. Okay, 7, sometimes you go to 1 and sometimes you go to 4. False. They get no choice. That x has to go to just one y value. Okay, so this one is not a function. All right, there's no choice. X does not get a choice in the matter. It has to go to only 1. And then the third one, if we're to think of this graphically, vertical line test, it's going to hit here at 2 points, can't hit here at 2 points. Okay, this fails, I'll say VLT for vertical line test. So because it fails, not a function. Because this is the same thing. If I'm at, what's this, 1, 2, 3, we'll say it's going through here at 3. Saying, okay, if I put in x is 3, sometimes it goes to a positive 2.5, sometimes it goes to a negative 4.5. Okay, 3 does not get that choice. 3 has to go to specifically one y value. That's why it fails the vertical line test. All right, so again, a relation is simply a set of coordinates. All right, there's no special rules on it. You list out a set of coordinates, that's a relation right there by definition. But for a relation to take it up a notch and be considered a function, it has to satisfy one x input goes to exactly one y output, passes vertical line test. If I draw these egg shapes, it's not going to have choice. X doesn't get to decide. It's going to go here or here sometimes. It has to go to only 1. All right, next thing is domain range. So domain, possible values for x. So your input, okay? Think about this alphabetically. D comes before R in the alphabet. Domain is the x, range is the y. All right, whatever you have to do to remember this, because now you're going to be asked questions, or I'll ask you, okay, what's the domain? What's the range? Can't be any hesitancy. Okay, which one's which? All right, domain is first, domain is x, range is y. Okay, so you could be given a problem that says, okay, find the domain and range. They could give you a table, they could give you a mapping diagram, or they could give you a graph. They'll say, okay, what is the domain and range of this? And we can talk domain and range of a relation. Okay, there's domain and range of a function, but we're not even going to limit it to just functions. We can have domain and range of a relation. All right, so the domain is represented by a set, and so we use squiggly brackets around a set of numbers. So for this one, my domain, my x's are just 1, 2, 3, 4, 5. So it's a set of numbers. It's not a coordinate. It's just listing out a set, and we use those squiggly brackets to define what our set is. Then our range, again, is just a set of numbers. But our range on here, we have 2. We don't have to write 2 3 times, even though it shows up 3 times. Our range is only 2 and 3. You only have to list it out 1 time. Even if it duplicates itself, you only have to list it 1 time. With our mapping diagram here, okay, mapping diagrams, domain is always on the left, range is always on the right. Okay, it's always set up this way. Even if it doesn't say it, domain is always on the left. So domain is going to be -9, -5, 1, 7. Range is exactly what's listed, 1, 4, 5, 8. Even though 7 goes to 1 and 7 also goes to 4, it's still a range of 1, 4, 5, and 8. And then with a graph, so again, domain represents all possible x values. Well, I can see right here, the furthest left this goes, 1, 2, 3, 4, is here at -4. And then it's all values going to the right positive x direction from there. So I could represent this with interval notation. I could say -4 inclusive, because there's a point right here at -4, all the way out to infinity. I'll put a parenthesis around infinity. And then my range, if I think of up and down, I can see that this is continuing to get higher and higher as we go positive x direction. And this is continuing to push down as I go in the positive x direction. And so this is -infinity all the way to positive infinity. Okay? Or you could simply write that as all real numbers too, if you want to write it that way. Okay, but that sideways parabola is continuing to get taller up and down. If you want to think of it that way, it's expanding up and down. So it's going to eventually, once I go out to a positive x to infinity, it's going to be a y to infinity and -y infinity. Okay. Find the domain and range, then say if it is a function. All right, well, real quick, to determine if it's a function from a graph, we could just do vertical line tests. Yeah, if I drew a vertical line on this, no matter where I draw it at, it's only going to hit at 1 point. Same thing here. It's only going to hit at 1 point. There's nowhere where I'm going to hit more than 1 point. So, yep, I can say this one is a function. And this one is also a function. This red line on the graph on the left, we have some black points that are plotted, but then the red line connecting them means any point in between there is also included. So really, this has arrows, even though they're not written on here, that this is continuing on beyond what my graph even shows. Okay, so my domain on this one, possible x values, it's going to keep going out here all the way to negative infinity, keep going all the way out here to positive infinity, because it's continuing on, it's getting wider. And so my domain would be all real numbers. Okay, or you could write an interval notation, negative infinity to positive infinity. My range is limited though. It's never going to go above, it's never going to get up here. It's always going to be from -2 and down. So this is -2 inclusive, because I have a point right there at -2, all the way to, and let's back it up. Let's go negative infinity to -2. We always want to write them in order from smallest to largest. So negative infinity is the smallest it's going to be, and it's going all the way up to -2. Now, the second graph, if you want to pay close attention, you could see that this has an open circle, and then this is closed. So this one has points at the ends of our graph. Those red lines did not have points at the ends. Because it didn't have points, we're thinking we put the arrows on there. This one does not have arrows because this is a defined interval. It's saying, okay, it goes all the way up to -3, but it doesn't include -3, and it goes all the way out to an x value of 1, but it does not, but it does include 1. So my domain on this one would be -3, not inclusive, all the way to 1, inclusive, because of the open versus closed circles. And then my range, it's only going from here at -4 all the way up to here at a y value of 0. And so this would be -4 inclusive all the way up to 0. And this is inclusive as well because it is closed right here. It does touch right there at the origin. Okay. Domain and range of this one. This is basically just a scatter plot. It's taking a set of points, a relation, and just putting those specific points on there. You can see there's no line that we could have that would connect these, not any sort of straight line or curved line. Like this one's a mess, and it fails right here. Okay, there's points right there. I'll get those. Okay, so this one is not a function. This one passes, so we'll say this one is a function. Domain of a relation, we're simply going to list out all the x values. So I have an x of 0, I have an x of 1, I have an x of 2 right here. And I have an x of 3 for this point. So 0, 1, 2, 3. So in this domain, I have these specific points, and I'm not writing it as an interval because there's not 0.5 is not included in this. Because there's no point that matches up. If I put x as 0.5, there's nothing in there. And then my range is simply all the y values. So I know I have 1 for these two. Both of these have a y value of 1. I have -1 for this one. I have +4 for this one, and 0. The graph on the right, I have a closed circle. So this one's closed. This one's open. So we have to pay attention to that. So my x values go from a -3 inclusive all the way up to 2, not inclusive. My range goes from a -5 inclusive all the way up to 4 inclusive. So we're thinking just up and down. Okay. I got one more slide, but I think you guys got it. I'm just gonna just talk through this slide real quick. If I want to find the domain and range of this one, okay, I can say, well, first off, it's not a function. This one is a function. I know my domain is going to go from, so my domain is from here to here. The range is from here to here. Okay, and not a function. This one, my domain, let's go real quick on this one. Domain is from -4 inclusive all the way out to infinity. And then my range is from 0 inclusive all the way to infinity, because this is going to keep going up and up and up all the way up here to infinity. Okay, and this one is a function. Okay, I think you got it. We've done enough examples with it, and you're going to do more here with the worksheets. All right, so kind of a lot of talking on my part, but I want to make sure that you have a good foundation to be able to build from as we progress through these next few days.